All right, guys, welcome back to videos with Miss Lastly, whatever we want to call them. I was going to think of a cool name and then I didn't. So here we are. Videos with Ms. Lastly. All right, so we are still in Unit 5, Graphing Trig Functions. Today we're going to look at inverses of both sine and cosecant. We're going to discuss the concept of an inverse. We're going to find our restricted domains for sine and cosecant, and we're going to do some practice using unit circle inverses, and we're going to do some practice with non-unit circle inverses. So if this is a lengthy video, I apologize. As you can see, we are covering a lot of stuff. So here we go. Okay, so first off, we're going to look at we're just going to talk for a second about the concept of an inverse. All right, so when you're doing normal functions, let's just say like the quadratic function. All right, the inverse of the quadratic function is basically when you put the y values in place of the x. All right, so here's a quick way. Let me just do a little doodle real quick. Okay, so I was gonna draw it all by myself, but then I remembered I had this really great visual that we actually used earlier in the year. Let's zoom in a little bit. Zoom, zoom, zoom. There we go. And it's interesting to look at. So when you have an original function, so I know this is kind of stupid because it's got like apples and bananas, but all right, your function is the apple, right? The original function. All right, so if you put the apple in, it gives you a banana out. All right, well, what inverses do is if you take the banana and you put it into the inverse, it's going to give you the apple, which was the original thing. So thinking about these as x and y's. All right, this is x, this is y, this is x. All right, so in the original function, the internet is so slow. It's not loading my writing. Okay. Now it's loaded. All right, so the apple is our x, the banana is our y. All right, so if you have a regular function, just f of x, you plug in the apple, you get the banana. All right, with inverse equations, you're plugging in the banana to get the apple back out. All right, so that's kind of the relationship. So when we're talking about trig functions, all right, because our trig functions are a little bit different than, say, a normal quadratic function where x's and y's are the same types of numbers, right? X is a number, right, negative infinity to positive infinity, and y is also that same type of number. It doesn't really look that strange, but when you're dealing with inverses with trig functions, x and y are two different types of numbers, right? X is generally going to be either a degree or a radian value, whereas y is going to be a coordinate, a point, like a number. All right. So when you're doing inverses with trig functions, it's going to look a little bit different because, right, instead of normally in trig functions, we plug in a degree value for our x, we're going to be plugging in a point for our x into the inverse, and it's going to spit out an angle measure. So it's opposite of what we're used to. And we're going to look at that a little bit closer, but just remember, this is the concept of inverses, right? So normally, whenever you're plugging something into original equation, you're plugging in an x, you're getting a y. The inverse equations, it's the opposite. All right, so we're going to start off by graphing the sine function, and then we're going to look at the inverse sine graph and talk about some key features. All right, so first, just graphing sine. We can do this. This is no big deal. All right, so I'm going to fill out my little chart over here. So I have 0, and then 1, and then 0, and then -1, and then 0. All right, so I'm going to try and find the middle here. I don't know, this looks kind of like the middle. And this looks kind of like the middle. So we're going to do 1 and -1. And then we have 1, 2, 3, 1, 3. All right. I probably can't fit everything on here, but that's okay. I don't want it to be too squishy because then you won't be able to see what I'm doing. So that's fine if we can't fit all of the points. So 90, 180, 270. I'm just going to extend this so I can get 360 over here. All right, and then same thing right here. So -90, -180, -270, boop, and then -360. All right, so then graphing my beautiful sine. Sine is my favorite. I don't know if you should have a favorite trig function, but sine is my favorite. All right, so I just think it's beautiful. I don't know, I like it. I don't know. I like the sine function, like not just graphically, like, I don't know. For some reason, I really just like sine. I don't know. I don't know if that's a thing that other people like think about. Like, I don't know, just I like it. Like I like SIN, like I think it looks nice. Like it's, I don't know. Whatever, it doesn't matter. Here's our sine function. All right, so here we have our sine graph. Now, two things I want you guys to notice. Number one is that the sine function does continue to go in both directions, and it does what we call oscillate, which means to bounce between two values, right? So the sine function graph is going to continue in both directions forever, and it oscillates between -1 and +1 on the y-axis. So it's bouncing between those values. All right, so if we were talking about limits, which you guys have talked about limits before, your trig function, sine and cosine anyways, they don't have a limit. The limit does not exist because it's not approaching any single value. Sine and cosine are approaching 1 and then alternately -1. So there's no limit, there's no end behavior for these graphs. They oscillate back and forth forever. Another thing I want you to notice is that this is not a one-to-one function. So pulling vocab back from chapter 1, a one-to-one function is something that has the original equation and the inverse equation both being functions. All right, sine is a function, right? The original sine graph that we have right here is a function. It passes that good old trusty vertical line test. But to check to see if its inverse is a function, we use that horizontal line test, meaning if we take a horizontal line and we move it up and down the graph, if it only crosses once, then we say that the inverse is a function. Well, looking at this, clearly it does not pass a horizontal line test because it crosses my horizontal line multiple places, right? Forever and always, it's going to keep crossing with that that horizontal line. So sine is not a one-to-one function, all right? Meaning its inverse is not going to be a function. But that's bad for us because we're going to be doing a lot of work with inverse sine as like a function. We're going to be solving equations once we get into our next chapter. And if you have like a problem like this where multiple values repeat, which is what's happening, right? We're getting, just look at 0, right? Right? Everywhere we cross that y = 0 line, there's multiple x values that have a y value of 0. And so if we were trying to solve this, say for x, right? And we have, a y value of 0, well, there are infinite many solutions for this problem, and that's bad. So what we do is we do something called restricting the domain, meaning we put a limitation on what we're allowed to call for our x values, where we're allowed to pull x values from. All right, now with sine, so I'm going to try gently to get rid of all this green stuff. Oh man, all this green stuff. I can do it, I just have to be gentle. It's so nerve-wracking. I don't want the whole thing to disappear. Oh my gosh, that was great. Okay, so I got rid of all the green. Okay, so we have to, like I said, we have to restrict our domain so that we never repeat any of our x or y values. All right. We also want to make sure that we have the full range of values. We want to go from -1 to +1 without repeating anything. So generally people say, okay, we'll just start at 0 and then go until you get both positive and -1. So let's look at that. All right. So I just highlighted starting at 0. I had to go up to get to +1, then I went down to get to -1. The problem is I repeated values, right? I repeated 0 at the very minimum, right? But there are other values that I repeated. So that's not going to work. Okay, so we can't just say start at 0 and then go until you get to both positive and -1. That's not going to work here. All right, but we can do it. It is possible. We just have to pick a different chunk of the graph. And maybe you guys are able to see this right now. Maybe you can't see it. But the easiest and most obvious chunk of the graph to pick is this chunk right here that goes from -90 degrees to +90 degrees. All right, we hit both positive and -1, and we have the full kind of span of values without repeating anything. We don't, right here in this section, from -90 to +90, we do pass a horizontal line test. So if we ignore the whole rest of the graph and just look at that section, it passes the horizontal line test, which tells me I'm not going to repeat any values in this section. So when we're doing inverse sine, we're only going to be looking at values from -90 to +90, which is our quadrant 1 and right below it, quadrant 4. All right, so we'll write this down. So our next thing, so restricted domain for inverse sine, we'll just say for sine, because we're not really talking about inverses all the way yet, right? This is the graph of regular sine. All right, so we're restricting our domain for sine to -90 degrees, +90 degrees. Oh, let me move my head. Where's my mouse? There it is. Ta-da. Okay. So we restrict our domain for sine to go from -90 to +90 degrees. Now, if we were in radians, right, we should know our radian measures, but this would be -pi/2, pi/2. Okay, so that's the first thing we have to know. So first thing we need to know for sine is that when we're doing our inverse for sine, we're only dealing with this section of the sine function or the sine graph. Okay, for two reasons. One, we don't repeat, right? So number one, no repeated values. And number two, we have a full range, right? -1 to +1. Again, let me move my head. All right, so we have no repeated values in this section, and we have a full range, meaning we go from -1 to +1. All right, that's the reason why we chose that interval. Now, going to inverse, all right, so scrolling down, I know the writing is taking forever to catch up. Okay, I'll just move my head up there and then scroll down. Okay, so inverse sine function. So first we're going to look at notation. So we have a very familiar notation, hopefully, this sine to the -1. All right, anytime you see something like this where it's the function and there's a -1 and then the parentheses, this is indicating it's an inverse. Now, please don't get this confused with something like this. All right, because one means inverse, one means reciprocal. So sine with the -1 before the parentheses, that indicates inverse, whereas the one I just wrote below, where the -1 is on the outside, so you have sine of x and then a -1 on the outside, that's indicating reciprocal. So this -1 right here is an exponent. All right, so it's an exponent of -1, and we know that negative exponents mean reciprocal, so it's flipped upside down. So this right here is actually cosecant of x, right? So it's the reciprocal of sine, so it would be cosecant. Oh, I don't understand why my internet has to be so bad. Anyways, so that's our first symbol. Now the second one is a little bit strange. So if you look next to it, you can see or y equals arc sine of x. All right, so that's another notation for inverse for our trig functions. And it's kind of an interesting story where it comes from. It's not really that important, but it basically is because when people were typing up math, when they very first got like typewriters and things, they couldn't do the exponents. So they needed a different way to write the inverse, because in trig, you do inverse a lot. With other functions, inverses aren't that important, maybe with logs and exponentials, but truthfully, you don't really come across other functions and their inverses very often, but it does play a big role in trig. So they needed a way to do the inverse with not being able to use the exponent on like a typewriter. So they made the symbol arcsine to represent inverse for sine, since there was just one straight thing in it, so it typed well. But anyways, it's still kind of used today. So if you do see the symbol arcsine, just know that that does mean inverse sine. All right. But yeah, so that's just a little history lesson. I looked it up because I was curious what the difference was, and there is absolutely no difference between sine to the -1 or arcsine. They're the same thing. Okay, so moving onward, so that's our symbol for inverse, for our sine function. Now for cosecant, it's the same thing. So we are kind of covering cosecant also when we're doing this because sine goes with cosecant. They are reciprocal functions. So when we said restricted domain for sine is going to be -90 to 90 and pi over 2, negative pi over 2 to pi over 2, it's the same for cosecant. All right, so you can write that if you need that, if you wouldn't have thought of that on your own. It's also the same for cosecant. So we're working in the with sine, and its reciprocal is the same with inverse. Okay, so let's look at the graph for inverse. It's kind of unfortunate that we have to graph this, but you don't really have to. Like, it's not gonna be on a test or anything, but I think it's nice to show you guys what the graph would look like. I think they do some of it in calculus for like a day, and so maybe just to introduce you to what it looks like. But it's not super important. I never had to graph inverse trig functions when I was in school back, you know, like 5 years ago, because it wasn't that long, because Miss Leslie is super young, obviously. Anyways, so remember, we are swapping all of our x and y values. All right, so if it was an x, it's now a y. If it was a y, it's now an x. That's what inverse does, which means that my x-axis is now going to go from 1 or -1 to +1. All right, so we have -1, +1, and our y-axis is now the degrees. So our y-axis now became the degrees of our function. So we have 90, 180, 270, 360. Same thing down here, 90, 180, 70, 360. All right, and now I'm just going to draw my dots and do my sideways S. Okay, so here's my graph. All right, so we have that sideways sine wave. All right, and remember, when we're doing this inverse, really we want to kind of zoom in on just this section of the graph, right? So we hit that -1 and we go all the way to +1, and we don't repeat any values. So that section right here. All right, so domain and range. So just looking at our inverse graph, right? Not normal sine and sine, just the inverse sine. So our domain, our x values range from -1 to +1. And our range is -90 to +90. Okay. Okay, so that's where we're at. Now we're going to move into actually doing some problems where we're going to use this. My advice is to either have your unit circle handy, or right here what I have is just the, where's the mouse at? There it is. So this is just the first quadrant with my values in it. This is something to really have handy. Now, eventually I would recommend being able to do this without having unit circle values in front of you. But when we're practicing at first, it's definitely a nice idea, and it will feel more natural if you can kind of see the chart, and then maybe it'll help make some sense. All right, so just to reiterate, all right, normally with the trig function, this is how the setup kind of goes, right? So it's trig function, trig function, whether it's sine, cosine, tangent, whatever, of some angle equals a side value. Well, we won't do side value. We'll put coordinate. Yeah, coordinate. Really, it is a side value, right? It's a side length because unit circle is just a bunch of little triangles, so it's a side of a triangle, but that's fine. You can't even see it. All right, so like I said, sorry, I'm like so out of it. I've been having to pause the video, wait for the writing to catch up, unpause it, so I'm losing my train of thought here. All right, so now that we have, the writing has caught up. All right, so a normal trig problem is trig function of some angle equals some coordinate. When we're doing inverse, all right, it's the opposite. So it would be some trig function with the -1 of some coordinate equals some angle. All right, so make sure you know the difference. All right, so when we start doing these practice ones, make sure you, like I said, can see the difference between the two. So regular trig functions, when you're solving, it's the trig function on the outside, some angle in parentheses, whether that angle is given to in degrees or radians, and you're supposed to spit out a value, a coordinate. All right. Inverse trig functions, you have your trig function on the outside with the -1. It's going to give you some coordinate, and you need to figure out what angle has that coordinate. All right, that's the difference. So let's look at a couple unit circle ones. All right, which is why I have my little unit circle table right here, because that is going to make things a lot easier. Okay, so for number 1, it says arcsine of -square root of 3 over 2. So arcsine, that it means we are doing inverse. All right, the -square root of 3 over 2, that is our coordinate value. So we're trying to figure out what angle has a sine of the square root of 3 over 2. So we're going to go to the table, we're going to look in the sine column, and we're going to look for square root of 3 over 2. Okay, so we have our 60-degree angle is square root of 3 over 2. Now the problem is it's positive. We need -square root of 3 over 2. All right, and that's where our range that we're allowed to use, that -90 to +90, that's where it's going to come into play. So we can only pick values between -90 degrees and +90 degrees. All right, well, +90 degrees, that's quadrant 1, right? That 0 to +90 is quadrant 1, which is the values that we have right here in our chart. All right, so we know we're not going to be in the first quadrant. We're not picking anything between 0 and 90, which means that we're picking angles in that fourth quadrant, which is 0 to -90. Now be careful. Some people want to tell me that it's, so for instance, 60 degrees. So they think about, okay, well, what is 60 degrees in the fourth quadrant? Oh, it's 300 degrees. So this must be 300 degrees as our answer. And I have to say, wrong, because 300 is not between -90 and +90. 300 is bigger than 90, all right? So that doesn't make sense. All right, what you would tell me is the negative angle that matches up with +60. Well, it just so happens that it's -60, all right? So for this one, we would say arcsine -√3 over 2 is going to be -60 degrees. Or you could put -π/3. It doesn't specify if we're doing radians or degrees, so you can pick. We'll just list both. All right, so the answer is equals -60 degrees or -π/3. All right, so see how we did that? We were given a coordinate and we needed to find the angle. That's inverse. All right, let's go to number 2. Now this is a 2-part question. All right, if you always want to solve what's inside first. So the thing that's inside the most is what we're going to find, and then we'll work our way out. So on the very inside, we have inverse sine of square root of 2 over 2. All right, so we need to go to our chart and we need to look, okay, what sine, what angle, right? So we're looking in the sine column, right? We're looking for square root of 2 over 2. So what angle has a sine value of square root of 2 over 2? All right, which is right there. It's our pi over 4 or 45 degrees. All right, well, it's positive, right? We have positive square root of 2 over 2 in our problem, so we would say that this is just 45. We don't need to do anything funky. It's positive, so it's just our first quadrant angle, which is 45. All right, so that's the inside piece. Now we still have this other cosine on the outside, right? We have this cosine hanging out right here. So this is, like I said, a two-part question. So now we're gonna do what is the cosine of 45 degrees. All right, so we're solving like two questions in one. We have to do the inside piece, we got 45 degrees. Now we have to do cosine of that 45 degrees, which is also the square root of 2 over 2. So our final answer for this one is square root of 2 over 2. All right, moving on to number 3. So again, we have a two-part question, but this time the inverse is on the outside, right? We have cosecant inverse of secant of 240. All right, so first thing we need to do is we need to figure out what is the secant value of 240 degrees. Now, since we have this nice unit circle chart over here, I'm just gonna kind of cheat a little bit. So 240, all right, those are our 60-degree angles, all right, but it's in the third quadrant. So 240 is in quadrant 3, all right, and 240 matches up with our 60-degree angles. All right, so I'm going to go to my thing and I'm going to look at the secant value for 60 degrees and just make sure it's negative because in the third quadrant, secant is negative. All right, so that's what I'm going to do first. So I go over here, I look at secant of my 60 degrees, all right, and I got 2, so I'm just kind of like using my chart here. All right, so this is then going to be -2, right, because we have to make it negative because it's in quadrant 3. All right, so the secant value of 240 is -2. All right, now it's asking us to find, boop, boop. All right, it's saying, okay, now we're doing inverse. So it's asking us for what angle do we have a cosecant value of -2. So we're going to go to the cosecant column and look for a 2. All right, and we see that that happens at pi over 6 or 30 degrees. All right, so now we're looking, okay, cosecant 2, that happens at 30 degrees. Now it's a -2, so it's not going to be 30 degrees. So we have to figure out what that would be in the fourth quadrant just by making it a negative angle. Because remember, we're not going all the way around the circle counterclockwise. We're just kind of going backwards from 0. So we would say that this right here equals -30 degrees. Or you could say it's negative pi over 6. That's our answer. Okay, so that's inverse. All right, so those are the 3 different types. You can either just have a straightforward one where it's just inverse sine or arc sine of something. Those are pretty straightforward. Those are easy. It's one step. The other ones you can see is when you have like number 2, the inverse is on the inside. So you do the inverse first and then you do the trig function that's on the outside. Or you could have ones like number 3 where the inverse is on the outside and the normal trig function is on the inside. All right, so just these are the 3 different types. Just make sure you can do all 3. Now the last piece is inverses when you're not on the unit circle. All right, so we're only going to do one of these just for the sake of time. So I'm going to do, there it is. I'm just going to do number 1 and then in the video, and then I'll fill out number 2 in the notes if you want to go back and look at it. It's the same technique. Okay, so here it's giving us, it wants us to find the tangent of this, whatever angle this is. So cosecant, inverse cosecant of 8 over 3. Since this is not the unit circle, we don't know what angle has a cosecant value of 8 over 3. So what we need to do is we need to sketch a triangle. Now, there was a reason why I drew my triangle in this way, right? So it's saying it's inverse cosecant and it's positive 8/3. that tells me that this is in the first quadrant. So I drew my triangle so that we had a first quadrant triangle. If this had given me -8/3, I would have drawn my triangle so that it would have been in the fourth quadrant. All right, so when you're doing cosecant and sine, your only two options are first quadrant or fourth quadrant. So if it was -8/3, I would have drawn my triangle basically upside down, right? So that it would have been in the fourth quadrant. All right, now cosecant is hypotenuse over opposite. So my hypotenuse is 8 and my opposite is 3, right? This is always my angle right here in this corner. Okay, I want to know what is the tangent of this triangle. All right, well, I need to do Pythagorean theorem to find my missing side. So I have 8 squared minus 3 squared equals x squared. All right, so really quick, I'm going to go to my calculator. 8 squared minus 3 squared is 55. Okay, so I have 55 equals x squared. So then I square root both sides. All right, and since I'm in the first quadrant, I know that my x value has to be positive. So this is going to be positive square root of 55. All right, now I'm going to find the tangent of this triangle. That's the final thing that I have to do. All right, so I need to find the tangent of this triangle. Tangent is opposite over adjacent. So this is 3 over square root of 55. Rationalizing my denominator, always, never leaving a square root on the bottom. I get 3 square root of 55 over 55. All right, so for ones like these, you're going to set up your triangle. All right, you're going to label it with the information that you're given, and then you're going to find the trig function of whatever it's asking. So this one was tangent, so I found the tangent of this triangle. All right, so that is it for today's video. I will see you guys in class.